Great. Welcome everybody. Happy Wednesday. I hope that your week is going well and not getting too overwhelmed with end of semester chaos yet. I know it's gonna hit us pretty hard and pretty fast here, but I will do what I can to make things as smooth as I can make them for you. Just a couple of quick comments. First thing is, don't forget that there is homework due tonight. A lot of times we don't have Wednesday homework. This week we do have Wednesday homework, but the upside of that is that there will be nothing due on Friday. So this is the last assignment for this week, and on Friday we will have no homework due. The next assignment after today will be due on Monday. So all of this is in Canvas, and the deadlines and problems are all listed there, so feel free to take a look at that. I'm going to do a couple of the problems that have ended up on my whiteboard here. I'm going to start off with this today. So we're going to actually start with the homework. If you've got your homework that's due tonight somewhere handy, I would be glad to help you out with that. Did you have a quick question? Yeah, what do you want me to add? 42. 42, okay, great, sure. We'll start with that. If I don't get through everybody's question of everything on the homework, I also want to remind you that I do have office hours, but I sent you an email to let you know that I need to change my office hours today. Just for today, I am going to do one big session from 5:30 to 8. I'm not going to take a dinner break at like I normally do at 6:30. I'm just going to stay till 8, but then I'm going to leave. The homework is still not due until 10, but I will be gone after 8. I'm not planning to come back tonight. So leaving campus a little bit early, but I will have quite a lot of hours here. And we're also going to go over some of the homework anyway. So I think it'll be okay. Another thing I just want to give you a heads up about, guys, because we're heading into another weekend where you might have some free time. Just this morning, I uploaded the midterm 3 resources folder. So if you go into Canvas and you look at that, you'll see that that folder is ready for you to start browsing through. When is the 3rd midterm? It's actually 12 days from now. So it's still a little ways off. It's going to cover chapters 6, 7, 8, and the first 5 sections of chapter 9. So that's almost all of chapter 9, really. We've already covered chapters 6, 7, and 8. We're done with all of that material, and we just have to do some stuff this week and next week on chapter 9. And that will take us pretty close to the end of the semester, and it will get us ready for our exam. There's a sample midterm, there's a review packet, there's a review session to watch. All of that good stuff is available as well. Yes, Josh.
The final's every chapter, right?
The final is comprehensive, yes. What you're going to find is that if you kind of double down on preparing for midterm 3, there's a whole bunch of stuff from earlier in the semester that comes into that, right? Doing null spaces, finding determinants, eigenvalues and eigenvectors, a lot of things, vector spaces, right? Any of that stuff, basis, dimension. That stuff is still with us, isn't it? Right? It's still here. So I think if you work hard towards midterm 3, then on the following week, when we're getting ready for the final, you won't have so much to do. There may be a few things from earlier in the semester that you need to go back and sort of check yourself on. But for the most part, I think you'll be able to have a reasonable time getting ready for the final as well. Okay. I think those are my main announcements. Slightly different office hours today, homework due today, and then I'll be around on Friday. It's just we don't have any homework due on Friday this week. So, any questions about any of that? Okay on that? Okay, great. Let's actually start off today with some of the homework. Let's grab that if you have that somewhere nearby. Let's start with problem 24 on the homework that is due tonight. This one is a little messy. I just cannot sugarcoat that at all. So this is problem 24 on today's homework. D times D plus 3 of y is equal to x times 5 plus e to the x. I actually would recommend that you just simply multiply this out anyway. It's just 5x plus x e to the x, just as well to do that. So this is an annihilator type of problem. We have 3 steps to the process, yeah? So step 1, this is where you write down the auxiliary equation. You get some old roots that then allow you to put down the complementary function. So the auxiliary equation is easy enough. You just change the d's to r's. And once you've done that, you get your old roots, which are 0 and -3. These are old roots. Okay, and so then we can write down the complementary function. I think we've had a lot of practice with this already. So C1 times e to the 0 plus C2 times e to the -3x. Let's put a box around that so that we can find it later when we want to put everything together at the end. Okay. So far, so good. This is, first step is not too bad. Okay, no repeated roots, no complex roots. It's pretty simple. Okay, now step 2 is where we find that it gets a little messier. We have to write down an annihilator for the big F over here. Could somebody remind me then, what is the annihilator of, let's just work on the 5x part. What's the annihilator of 5x? D2, yes? D squared. Okay, yeah, D2 or D squared, exactly. So 2 derivatives of 5x, we'll get rid of it. Remember, when you're figuring that out, you don't even worry about the 5. And if you have a brain fog and just can't think of it, go to your table, right? That table of annihilators will tell you that it's D squared. What about the annihilator of x e to the x? Yes.
D minus 1 squared.
D minus 1 squared. And again, you can grab that out of your table of annihilators. Now, what do I do with the 2 annihilators that I found right here? Multiply them. Now, that's something that's a little bit counterintuitive. There's a plus sign right here, but down here, we now need to multiply those annihilators together. Okay, so there's the annihilator, and we will get some new roots coming from this annihilator. And what are the new roots going to be?
0, 0, 1, 1.
So from the d squared, we get 0 and 0, and from d minus 1 squared, we get 1 and 1. So those are my new roots. And so let's go over here and write down the form of the particular solution. So the yp of x. If somebody wants to give that a try for me, go ahead, Alexander. Ax, good.
Plus bx squared.
Plus bx squared, great.
Plus, I'm thinking out, sorry.
Oh, that's okay. Does somebody want to jump in? Yeah, go ahead, Tina. C e to the x, good. And then the last term? The x e to the x. So the root of 1, right, gives us the e to the x. And we stack an x the second time we see it. You do want to be careful because the 0 here, the new roots that have the 0, keep in mind that that was already an old root. So you're stacking x's even from the very beginning because you had already seen that root in the complementary function in step 1.
I just want to use D because like.
Oh, D is maybe not the greatest choice because it reminds me of the derivative operator. I'm just going to use it. But you're absolutely right. It's maybe not a great choice, but I just want to use it. Okay, so there's my particular solution. Now, I need to solve, this is where the problem gets a little messy. I need to solve for A, B, C, and D. And to do that, I'm going to need to go back and plug that particular solution into the differential equation, which means I need to have 2 derivatives of that in my hands. So I'm just going to take 2 derivatives right now, right? Because this is really y double prime plus 3y prime. Okay, so I need 2 derivatives. So let's just take a couple of derivatives here before we do anything else. The first derivative is just going to be a plus 2bx plus c e to the x. And then I'm going to factor the d out and use the product rule. on the x e to the x, so the first term times the derivative of the second, plus the second term times the derivative of the first. And we just have to put that with the d term. Okay, so that's one derivative, and then I gotta go and do another derivative of it. So the second derivative here, well, now we have 2b, right? Pull down the 2b, and then the derivative of c e to the x is still just c e to the x. And the d term gets just a little bit messier again, so I again have to use the product rule on x e to the x. But then I also have to add the derivative of e to the x again. So it actually turns into x e to the x plus 2 factors of e to the x. That's the derivative of the second, that's the second derivative of the particular solution. Is this too fast? If I start going too fast, somebody's gonna let me know. Most of this is just a little tedious. It's not particularly, insightful to spend a lot of time on it. So now I'm gonna actually plug this thing in. Plug all this stuff in on the left side. Okay, so I got y double prime. I'm gonna have to write it down. So 2b plus c e to the x plus d times x e to the x plus 2 e to the x. All right, and then we have plus 3 times y prime. So I'm going to just triple every single term on the y prime line. Okay, and so now I am gonna end up using a little more space here. So I just tripled everything on the first derivative line. And now I'm ready to set that equal to 5x plus x e to the x. Now, on the right-hand side, I only have sort of 2 terms. But actually, if you think about it, on the left side, there are actually 4 types of terms. There's constant terms, so I'm actually going to try to emphasize this. There's a constant term. On the right-hand side, there's no constant term.
Linear term.
And then there's the x term, right, and we do have one of those here, 5x. And then there's just a plain old e to the x term, which we don't see one of those on the right side either. And then there's one copy of an x e to the x term. So I'm literally just taking what was already on the right side and just kind of spelling out a little bit more clearly the different kinds of creatures that we are going to see when I examine the left side. Everybody with me? So like, for example, on the left side, I'm going to ask myself, well, what are all of the constants? Right? They have to add up to 0, but I see that I have a 2b right here. Okay. And then I also have a 3a right here. So let's put that together. Those are the only 2 terms that are just constants with no x's anywhere around them. Right? So 2b plus 3a. Then I can ask myself, okay, well, what are the terms that look just like x's? In other words, what terms have x in them but no e to the x?
Bx.
6x.
This one right here, yeah, the 6bx. So let's write that down, 6bx. All right, great. Now I want to ask myself, what terms have just e to the x? Not x e to the x, just e to the x. So so e to the x, I've got a c right here. I'm going to skip over the x e to the x. I've got a 2d right here. Yeah, and then 3c, yep, 3c, and then what else do I have? 3d, exactly. So there's the e to the x parts. Okay, and then finally we have the x e to the x parts. And so I'm looking back from the left side, starting at the beginning. Here's x e to the x with a d in front of it. And then where else do I have? Right here, plus 3d, exactly. Okay, so there it is. And we know that this guy has to be 0. This guy has to be 5. This guy has to be 0. And this guy has to be 1, right? Where am I getting these? The 0, the 5, the 0, and the 1? That's just matching them up with the coefficients from the other side of the equation. Okay, that looks all right? This isn't so hard to solve now. For example, right here, this one is a pretty easy one to just do because you can just solve for b if you divide by 6. So b is 5 over 6. And once I know what B is, I can come back over here and figure out what A is. So I may as well do that right now. So if I put in, so A is actually negative 2/3 of B. Set this equal to 0, A would be negative 2/3 of B. And that's going to give me, I think, negative 5/9 when you simplify it. I'll let you guys check a couple of the little technical details here, but A should be negative 5/9. And then on the second part over here, so this is a 1 on the very last term, but it's actually 4D. 4D has to equal 1. So that's going to give me D as 1/4. That's the D value. So D is 1/4. This is all showing up here. So D is 1/4. And then once I put in 1/4 here, I should be able to solve for C. I believe it's negative 5/4 of D. I'll let you guys double check that. I believe this is negative 5/16. Okay, so those are the 4 numbers that we've been looking for. And if I've done all that solving correctly, now I can write down the particular solution exactly as it should be, plugging in these numbers. So A is negative 5/9, multiplied by X. And then the B has a 5/6 on it, and that's multiplied by X squared. The C has a negative 5/16, that's times e to the X. And then the D is 1/4, and that's X e to the X. So there you have the particular solution, specifically with all the numbers plugged in. And then I am going to be lazy in step 3. I told you guys you could do this too. You can just simply write down y of x is yc of x plus yp of x. That's the last step. You don't need to recopy any of that down again. What do you think? Pretty good? Any questions on that? Yeah, Raylene?
Something like this with an exam, can we just write that as an answer and we'll be okay with that?
This part, yeah, this step I've said before, you can just leave it like this so that you don't have to recopy everything down again. But you would have to do everything else. Like you have to do all of this, solve for ABC. This would be pretty brutal for a test question, actually. I probably wouldn't go quite this messy. Yeah, Josh?
So we get you an Algebra list on these?
Yes, that table, this table that I passed out, if you lost your copy, it's also on Canvas in the special handouts. I will be giving that to you on every test. Yeah, you don't need to memorize those. Okay, great. So that's 24. Any questions on 24? All right, now let's go to number 30, which was another question that you guys put exactly the same 3 questions up on the board that my first class did. So I'm thinking those must be the 3 hard problems that everybody wants to talk about. So let's look at number 30. This one is y triple prime plus 2y double prime minus 5y prime minus 6y, and that's supposed to equal 4x squared. Okay, great. So let's see if we can figure this one out. Actually, this problem is very much the opposite of number 24. Number 24, it's the step 2 that's a mess. On this problem, the hard part is actually step 1, because the auxiliary equation here is r cubed plus 2r squared minus 5r minus 6 equals 0. So when you're doing step 1, one of the very first things you do is write down that auxiliary equation. Okay. So far, so good. So one of the challenges here is like, how do you factor that? We don't, it's not a quadratic, so I can't just use some formula to get the roots. I'm wondering if you guys, did you learn in high school that when you have something like this and you're looking for the roots, the candidates for the roots, the possible roots, would be divisors of this constant term. Does that sound familiar at all? Not really? Okay, well, actually, so you could have any kind of like irrational roots, like some crazy numbers could be roots, but the candidates for the rational roots are divisors of of the constant term. So the candidates for R would be, so the divisors of 6 are these numbers here, 6, 3, 2, and 1. And you can also have their negatives. So there's actually 8 different candidates here. Yeah, Sebastian.
So how many roots are we looking for?
3.
It's a cubic equation, so I'm hoping that there might be 3 roots. And of course, that could be including repeat roots, it could be complex roots, right? So we're just gonna take a gamble that maybe some of these candidates actually work. To be honest with you, the best way to get the roots on this problem is to just guess some choices to try, right? It's actually not that hard. If you plug in, I'm just gonna spoil your fun for you here and just tell you, for example, if you plug in -1 into here, right? So you take -1 cubed plus 2 times -1 squared, and then -5 times -1, and then -6. What you get is -1 plus 2 plus 5 minus 6, and it totally cancels out. So this confirms that -1 is a root, right? Anything that is a root would be something you plug it in, it gives you 0. Okay. So -1 is a root, and that was one of our candidates that we could look for. Another one that works is actually R equals 2. Again, if you just plug it in, 2 cubed plus 2 times 2 squared minus 5 times 2 and minus 6. If you just work that out, this is just 8 plus 8 minus 10 minus 6. That cancels out completely as well. Okay. And finally, the last root that you can find, again, by just trial and error a little bit. So we had 2, and now -3 is another one that works. If you plug in -3, so -3 cubed, that's -27. And then 2 times -3 squared is actually plus 18. And then minus 5 times -3, and then minus 6. If you crunch those numbers out, you will once again get 0. Okay, so if you were sort of sitting at home, kind of fumbling around with this problem, not sure how to get the roots, what you have now seen me do is pretty much just wing it. And I just basically tried some choices that seemed likely to work. On a homework assignment, of course, I don't mind letting you kind of play with something like this. I don't want anybody thinking, oh, well, gosh, the next midterm is going to be terrible because I'm going to get roots I can't figure out. This is not what we're here to do in Math 250B, right? If I set up a problem that you can't find the roots for, then I don't get to even find out if you know any of the material that we actually did learn in this class. So I'm not going to be trying to come up with difficult factorizations. That's not going to be my objective. But it doesn't hurt one time to kind of remember something that is useful for factoring polynomials. These days, of course, you can just get a calculator to do it. Most of the time that won't have any problem factoring something like that. Okay, so anyway, if everybody's all right with that, we can now write down the complementary function, right? So that's going to be the next thing we would do. The y sub c of x. Can somebody tell me what it's going to be? Yeah, Nathan, go ahead.
C1 e to the 2x plus C2 e to the -x plus C3 e to the -3x.
All right, there we go. We just take the roots that we found in the auxiliary equation and write down those terms accordingly. Okay, so that's step 1. Great. So for step 2, everybody so far so good?
Yes.
Great. So for step 2, I need an annihilator for 4x squared. Do I have anybody want to tell me what that is? Let's have somebody else bring this up. Sebastian?
DQ.
Okay, d cubed, exactly. So you just ignore the 4, right? We don't worry about that. And the x squared, if you have a brain fog and forget what it is, just go to that table and it will tell you that it's d cubed. Probably most people would recognize that that makes sense because 3 derivatives of x squared is definitely going to give you 0. All right, and so your new roots here would be 0, 0, and 0. Those are the roots of d cubed equals 0. Okay, so can I get some help with the form of the particular solution? What would the form of it be based on those roots right there? This one's much nicer than the last one. Go ahead, Alexander. All right, fantastic. A plus bx plus cx squared. Notice that we're stacking x's when we have repeats of those roots. Beautiful. So this is the form of the particular solution. I am going to need 3 derivatives of it over here. So let's just take a few derivatives here. The first derivative would be b plus 2cx. And then the second derivative, if I take another one, it's just going to be 2c, right? And then the third derivative actually is just 0. So you just take 3 derivatives and it quickly simplifies down. And now you just have to plug those in on the left side of my equation, right? So we plug these in. I think I'll do that right here. And do it fairly quickly, guys. So y triple prime was already 0. Plus 2 times y double prime was 2c. And then minus 5 times y prime is b plus 2cx. And then finally minus 6 times the original y sub p, which is a, plus bx plus cx squared. And all of that is supposed to match up with 4x squared. So again, we're matching the left side with the right side here. And well, the right side is very simple. It only has an x squared term, so I can go on the left side and figure out where is the x squared. I see it right here, and it's got a negative 6c in front of it. So negative 6c, it better match up with 4. That's just by comparing the x squared terms. Negative 6c would agree with 4. And then the x terms have to cancel. So when I go to looking at the x coefficients, on the right hand side, I don't have any x coefficients. So then I look on the left side, where are the x's? Here's one right here. It's got a negative 10c in front of it. And then here's another x right here that has a negative 6b in front of it. All right, so that's the x term. And then we have just the constant. I'll just write it this way, const. The constant term on the left side, I have what, 4c minus 5b minus 6a. And again, that needs to be 0 because there's no constant on the right side. And you just have 3 equations and 3 unknowns. I think I'm going to stop for now and let you solve for a, b, and c. You can start with the top, figure out what c is, then plug it in here, solve for b, and then solve for a, and then you'll have your particular solution. Seem okay? Sorry. 10 million pictures of me running in front of the board. Okay, so that is part 30, problem 30. Great. All right, let's look at any questions on that? Everybody hanging in there? Let's try number 42. I guess I can just erase that now. We're going to do 42. 42 is pretty fast because they only ask you for the form of the trial solution. So they're not going to do the solving for A, B, C stuff. So 42, get this one up here on the board. D squared plus 4 times D minus 2 cubed of y equals 4x plus 9x e to the 2x. And the thing is here, all they want you to do is, it says actually determine an appropriate trial solution. So that's just the y sub p. That's literally just like this kind of thing. That's what it means. Trial solution just means what is the guess of the form of the particular solution. I know I've been using the words interchangeably. The form of y sub p, that is just what they call the trial solution. Okay. So we just need to go through we just need to go through the steps here. So step one, of course, this is simply, again, we have to write down the auxiliary equation here. R squared plus 4 times R minus 2 cubed. Anybody want to tell me what are the roots of that auxiliary equation? Yes, go ahead.
R plus or minus 2i
Plus or minus 2i.
and 2, 2, 2.
And then 2, 2, 2, exactly. Keeping track of repeats is important. So this is what we would end up with. And based on that, I can already write down the complementary function. So let's just go around, get a few different people to give me some of the terms here. Somebody want to tell me what would be the first term they want to write down? Tina. C1 cosine of 2x. Great. Somebody else want to take the second term? Elias?
C2 sine of 2x.
C2 sine of 2x looks good. Anybody want the next term? Yes, Josh.
C3 e to the 2x.
C3 e to the 2x. I love it. Next term? Alexandra? C4x e to the 2x. And the last term? Go ahead.
C5x squared.
C5x squared
E to the 2x.
e to the 2x. Looks good to me. That's the complementary function. I think everybody's getting pretty good at this, right? This part is not so bad. Okay, so that's the first step. And then we go to step 2. Here's where we need the annihilator. All right, so what is the annihilator of this right-hand side? We have to annihilate the 4x. What do we use to annihilate 4x?
D squared.
2 factors of d, very good. So d squared. Again, if you don't know where that's coming from, you can always go to the table. Right? That annihilator table will have that. All right, great. And then how about the annihilator of 9x e to the 2x?
D minus 2 x squared.
Yeah, this, right. So it's number 3 on the annihilator table. There's an x e to the 2x. So we're going to do d minus 2, but we're going to square it. Yeah, it takes a minute to get the letters in the table matched up with what you have. But this is what we should end up with here. Okay, so my new roots would be, well, just 0, 0, 2, and 2, right? Just give those 4 roots. All right, and so we can now try to write down the form of the particular solution, and I'm ready for 4 more volunteers. Alicia, do you want to try one of the terms for me?
C1.
Pardon me?
A.
Okay, I like to use A, and the thing is, it's not quite gonna be A, because you're going off of this root, but that root, oh, I'm sorry. No, that is correct, it is just A. Sorry, I was getting it mixed up with, I think, with one of the earlier examples where we already had seen that root. Okay, so A looks good. Anybody else wanna try the second term? Really?
Would it just be B?
How about B with an X on it, right? Because we're stacking X's when we see those repeats. So there should be a B and an X there. All right, looks good. And then anybody, Gus, do you want to try the next term?
CX cubed.
CX cubed.
E to the 2x.
Sorry, I'm standing in front of the work there. Yeah, e to the 2x, exactly. So the root 2 is now being repeated already for the 4th time. See, 3 times right here. This is now the 4th time we're seeing that same root. So we're just, actually the way I like to think of it is you just pick up where you left off. So you left off with an x squared, e to the 2x up here. So now down here, we just keep going. We pick up with the x cubed. Okay, and then what would be, we need one more term. Anybody want to jump on that one, Josh?
Dx to the 4th e to the 2x.
Sweet, dx to the 4th, e to the 2x. We just stack one more x there, and that's it. So this is the form of the trial solution. Okay, and thankfully, they're not asking us to solve this one. I mean, this is a 5th order differential equation. So if you actually wanted to find A, B, C, and D, we would now have to take 5 derivatives of this and then plug everything into the left side. Oh gosh. I would not want to do that right now.
Like extra
So-
credit.
That would be like major extra credit. I'm not sure it would be worth it. And I think I at least would probably get it wrong. Because it'd be so easy to screw something up. But anyway, that is how that works. Make sense? Any questions on, so we just did 3 of the homework problems for tonight's assignment. I think that was a pretty good choice of 3 problems to do. Anybody having any concerns with this section? In your engineering classes in the future, or well, really any class, you may sometimes hear this annihilator method referred to as the method of undetermined coefficients. Undetermined coefficients, and basically they're talking about A, B, C, and D. Those are the undetermined coefficients in the particular solution. It's just another name for the same thing that we're doing, that I'm calling the annihilator method. Okay, so don't let that freak you out if you hear that word in one of your future classes. Undetermined coefficients. It's just the same thing as this annihilator thing that we're doing here. Okay, don't forget, guys, that sometimes we cannot annihilate the right-hand side of our differential equation. So on Monday, I kind of gave you a backup plan, right? The backup plan was, well, there's another method here called variation of parameters. And for sure, everybody, so I sent you guys an email that had a document that was like a derivation of the U1 and the U2 formulas. And that's for your own reading pleasure. If you have an interest in it, you certainly could ask me questions if you have any. However, the main thing you need is to know the formulas for the exam, right? So you have to know what is the formula for U1, for U2, and for Y sub T. So I just wrote them up here on the board again so that we kind of highlight that again one more time today. Usually there's somebody in the class, every time I teach the class, there's somebody in the class who remembers these formulas wrong. So I want everybody, I would like 100% correct memory of those formulas if possible. Yes, Nathan.
And this method variation of parameters works for all linear differential equations all the time.
This always works. Now you have integrals to do. The integrals may challenge you. You never know, right? That could be a challenge. We're only going to do it though by hand and in this class for a second order differential equation. So I will not ask you to do variation of parameters in a higher order differential equation because it's just too messy to do by hand. You can do it on a computer, but I don't want to do it by hand. It's just too hard. Okay?
Yeah.
One of the other things that is a challenge with chapter 8 is you have to decide which method to use when, right? So sometimes annihilators makes more sense. Sometimes variation of parameters makes more sense. So what I would like to do for a few minutes right now, I'm going to pass out. This is another group work. We've been doing a fair bit of group work in the last few weeks. So I'd like to do some more of it today. My first class seemed to get a lot out of this. And there are only 2 problems on this group work, but I'd like you to try them. They will be solved by different methods. So we got different methods to show off here. And so yeah, go ahead and grab 2 or 3 people. You can come on up and see what you can do.
Really quick before I start the group work.
I gotta get this erased. Go ahead and talk to me.
I probably best if I write that out.
What's that?
It's probably best if I just write it out.
Thank you, Tina.
No, I'm gonna get done with this.
Yeah.
What if one of their functions was the x squared? And you ask them type 1, and there's probably one time. It's just a number, right?
Yeah, then you have something that we don't have an integration formula.
So that means it's pretty good.
Right. You would have a symbolic expression for E1, but you wouldn't actually know what it was. Yeah, that can happen. Yeah, that's something that we have to live with. If it comes up in the real world, we deal with that.
Computers.
That's right, use computers at that point. Where are my groups here? Are you guys big giant group of 5?
Yeah.
I've got Don, do you have a group, Don, yet? No, so let's get, maybe we can, the 3, maybe there's some space over here as well. Split into maybe 2 and, you can work together. Don, if you wanna come work with these guys, you can erase that. Come on up. Get everybody in a group. Gus, do you have a group? No. Oh, hey, guys, why don't you three just all work together?
Yeah.
I want you talking to each other, basically. That way you're not just. Yeah. You know what? It's amazing when you verbalize stuff and you talk out loud. I notice when I teach something, when I have to hear my voice saying it, I actually retain it better than if I'm just
We're not
thinking
using
my
any
thoughts.
requirements on that one.
It's actually a good idea to communicate. So I'll let you work all together.
This one, when we get the formulas for that, the first time.
How come?
Because you have 2 separate, you can't use 2 separate languages.
Correct, and actually even if it's just ln of x. Exactly, so you don't even have anything to annihilate the f with, so I agree with you, I would try the very. Start with step 1.
Yeah.
Still do that like
Yeah, like a cosine of x. Stuff like that, yeah, you would get sines and cosines. Actually, we did one in class. So what else come up?
Oh.
This is a complementary function.
To be determined. Be like you
I'm solving for the
y times y2.
which is
You add it together,
which is
and
a
then with that, that's being.
quotient, so we're gonna have to use.
Okay, well, I think we're supposed to start off with step 1, which is just to treat it like,
Right, step 1 is the first step. You won't be able to do the Wronskian until you've got the y1 and the y2 in your hands. So that comes from the roots of this equation that Elias is recommending. Yeah, so far so good. Good. Everything good here, guys?
Yes.
Take turns with, are you guys working on the same problem?
Yeah.
Oh, you're helping him.
Oh, yeah, it's Ron.
Oh, yeah.
Yeah.
Okay, excellent, excellent. And then give Danya a chance to take turns. with the marker. Around.
That's the first one.
If you pass her the marker, then you guys have to help her with what's right. Very good. Very.
And so U2 is just that.
That's true.
Also, this is why. So you just write exactly.
Yes. Yeah.
Y1 times X. So now.
Oh, wait, no, actually, Y2 is going to be X.
Wait, actually, no.
And so.
Y2 is going to be
The
X.
W is Y1.
This would
So you
be.
have the Wronskian part.
Yeah.
I'd really.
See how it's Y1 and Y2. So
This
it's
is
going
a
to be X. You know, that's what I'm just saying. Before I said it was going to be.
So there's an interval. And so
I'm doing the Wronskian.
he's doing the W part of the block.
Yeah, that's
correct. So just to get that out of the way right now.
Yeah.
That's where you set it up.
clarification.
Put this. And the second one was.
Yes.
Yeah.
Why? It's equal to.
Yeah, usually when I miss like a week of I was so behind. It was like back in chapter
Yes,
4.
I
It's like a whole week.
I couldn't. Oh, yeah, right here.
I feel you sometimes like I don't want to just lay in my bed.
So
But I have a class right before this. So it's like. So it's like.
the motivation to actually come.
I have a break, so I can.
Sorry, it's Y1.
Oh, we're in the same. Yeah, but I have a break.
But I have like an hour break.
Oh, yeah, I eat, so I just chill.
And so.
What's gonna be out?
Um,
So y'all be the
Oh, yeah, ethnicity.
Yeah, this is minus this.
Looks good, guys.
Yeah, what's guys reading? So this is about Y1.
These two on top,
Yeah.
and then below it is just a.
Yeah, so this is gonna be the.
Looks good.
Looks good.
Everything making sense?
Sorry.
All right, fantastic, fantastic, good job.
So we're gonna take this, we're gonna take this 80 minus.
Yeah, we just like barely touched it.
Barely touched it.
And then we did this.
Oh.
I'll find one.
Oh, yeah, so then you two is no negative. That's just, that's why. Yeah.
So we're multiplying, yeah, like this. Like
Wait,
cosmos one.
and then this is X. What's X?
Wait, I didn't write that down.
I think it's this.
So
As far as our.
What was that? Was that Y1, Y2, and then the derivative?
Very,
Oh, yeah.
Y1, Y2, Y1 derivative, Y2
you
derivative?
need to use the somewhere probably. There's also a table of intervals, so they, right, you might find that.
I think we're missing a two.
You guys are off to a good start. How are you guys doing?
Oh, no. It's the same thing. Negative 4F. I just gotta wait for this part.
So that's it.
What is the X? Oh, yeah, you're right.
So you want is
Yeah.
negative Y2.
Oh, yeah, five.
Y2. This is- Right. So you want.
Yeah, you start with this one.
Two.
At this point, it would be.
I think this one's like.
This one.
This is-
That doesn't.
So you'll end up with
That's-
over X, and then over that. Yeah, they do.
That would be the integral, and that would be in that table.
Really?
You guys
No,
have-
I'm pretty sure.
Yes,
Right.
I mean, I know this, but I'm pretty sure.
That's good, that's good.
Yeah,
Yeah,
well,
you
that's
choose
white
one.
line.
That doesn't make sense. Like literally everything else you can add.
And then
Gotta
they'll
be
be.
careful, here's an X and it's an X. They cancel. They cancel there, they cancel. How are you guys coming? Okay, well, let's get it straight down. We got this one times this one. And then minus this one.
Yeah, I've done it so much, it's
this
kind of
one.
just in my head, you know?
Okay. Oh, you know what? Here's a problem. So when you do the product rule on that, you're gonna get the derivative of this one times this one, which is there.
Yeah, but it's
Plus
still.
this one, we need X times the derivative. So there's gonna be an X
You can back
right
up.
there.
Check your paper.
Yeah, the
This
the
makes sense.
Wronskian should.
Instead of negative.
Oh, yeah, okay, so this cancels out, all right.
Yeah, it's gonna end up canceling
Yeah.
out and leaving you with something very.
Yeah, yeah, it needs negative one, yeah.
That's right. Is that what you got there?
No,
No,
I.
you
I was
just-
thinking
oh,
it's waiting.
And how is this canceling with X?
Oh, yeah, times 1 over
E to the negative 2X on top and E to the 2X on the bottom. It actually does not cancel. But the Wronskian over here is going to save you, or in a minute, it's gonna help out.
Yeah, this is the Wronskian, so Wronskian, I got, we got.
What is it you're doing here?
It needs a negative 4x.
Can you do that?
For the Wronskian?
Yeah, 'cause these are-
Factoring out the E to the negative 4X, I think that's totally fine.
We need to do the two native.
It's a minus, but you will have a negative. It's a negative 2 right here.
Like, you need to
So
cancel
this
that.
will get turned back into a plus again. But
Actually, we can probably do a
yeah, that's right. That's right. And now, actually, this cancels out. And the only thing that's left is this.
No.
Okay, but do you understand how I got this? Yeah, so you guys understand? Yeah, so like.
So, oh, you two.
This is canceling with this part. So this is gone, and this first part is gone. The only thing that survives is this one that's being multiplied. That's good. Good job, guys.
I missed the line.
Anybody need help?
You're fine, I think.
No, yeah. So this doesn't. So it looks like, I don't know what it is. So this is ln x over x.
Right?
You're right. You said
One over x?
Yeah, you said just take it half. You said the ln x and the derivative. Yeah, you have one over x. Yeah, you leave.
And this is just, yeah.
No, I put dx on the use right here, replace dx, right?
Oh, wait, no, it's just use ux.
Yeah.
U squared over 2.
Oh, that's the u like that. I've always had.
Oh, yeah, oh, I forgot the name.
Yeah, that's gonna be u squared over two, right?
We could put names.
Is that angle of u?
No, it's just over 2.
Oh,
This is squared.
That's your.
No, I'm saying you can bring this to in front. We can't.
No, it's not times 2.
Oh.
Wait, this one actually will cancel.
Yeah. It's just
One over x.
use of.
I think
Right?
on this one,
Yes. Or is it the only other way?
use the minus.
Yeah, we are.
Is one over x?
That's minus. That's actually going to be.
Also,
Yeah, because I think.
Well, if
I'm
you
messing
do
up.
it-
It's confusing.
That's what I was saying.
Okay, this one is
I'm
U2.
not even hard to- I guess not.
This one's U2, this isn't.
I think, isn't that one like XL and X?
And now
I'm
we're
getting
minus
no.
here.
No, I don't think so.
Yeah, that's it. Getting through YouTube is exactly right. Very good. Good job, good job. Now you just need to put it all together, right?
Everyone finish it off?
Let somebody else finish off. Yeah. How's this coming out?
Oh.
Oh, nice.
X, ln x minus x.
Oh, it's close.
Oh, you know what? You just took the derivative.
Oh, yeah,
You took the derivative of an ln of x, not the
X
integral.
minus x.
Right here. So the integral of ln of x, we need that. Do you have that table? I've given out all my spare copies. That table of annihilators and integrals has it. I'll just tell you what it is. It is in your table. So there's a minus sign here. And then this is just x ln x minus.
Oh, wait, no, you have an extra X.
Okay.
on the
And this
bottom.
one looks
Right
good.
here.
This one, yeah, U2 looks, that's U2
Oh,
and
yeah,
that looks
you
good.
can
Yeah, you
cancel
should
it.
have.
You got
rid of
U1,
the
you got
LN
U2, so now you just need
Yeah,
to
we
try
got
to plug it all in. Exactly. You're exactly right.
Mine would be.
Looking good. How are we coming along?
So we have all the parts here to do.
Hey.
To do
Yeah,
that.
yeah.
If you wanted to.
Uh-huh.
And then the
You
sum
know
would
how
be
to do
at
that,
this.
Rebecca?
No.
It's
Well,
been,
wouldn't it be like?
Like, I don't want to.
One over x and then basically times ln x, and then you just like.
I mean, you're gonna
take
do
the
the whole
product rule.
Y of x equals.
yeah, you can't really do the product rule on that, but this one can be solved basically by.
Oh, yeah, because the derivative of ln.
It is times x, but you want-
X, right, so this actually just becomes the integral.
Like so many words.
And then you have.
This is the same.
Two equations, so you just get 1/2.
You want to just start with this. And then just add this.
That
I'm
is
just
your
trying to get
U2.
it multiplied together.
And U1 looks good as well.
You
Excellent. Into wherever your y sub p is. So it'd be good to write that down. Just so you finish it all.
Be formal, right? We could just annihilate it.
It's a y
I think it's the same thing.
y sub p
You want to try it with the variation parameters?
y sub p x equals,
No,
and then
you
you
gotta
make these
Yeah, if you want Y, so it would be,
It's basically the perfect box.
y one is right here, e to the negative two x.
We were just like up there or something. Take that, combine it.
You can do that architecture for existing.
Do you have?
I think
Yeah, and then plus c two, which is right here.
Okay, but the second one, we don't have to do the because might have to do PC. My
Square.
This is degree of three.
Times x x.
It's gonna write straight. I'm just gonna go straight to R. R cubed.
And then that's your answer.
And then compare it with what
Y
we
squared.
asked.
36y. 36. We just did 36.
no, 36Y.
Y of x equals y c.
No, because there's no derivative on the y.
Oh, yeah.
Ooh, that should be y to the
You
fourth.
are 4. So we're saying this.
But they said- they
yeah,
said
I
that
think there's
there
actually
was
four derivatives.
Okay.
Yeah,
Cool,
he
I thought
said
we were
that.
gonna have to
You
do.
almost have to get glasses, magnifying glasses.
I'm just gonna be 9 and 4.
Actually, no.
We're that.
R squared.
So let's say it's just gonna be
forward.
R squared plus 9.
Okay, yeah, I see what you did. Yeah. Yeah, because I just figured like.
Add
this and multiply that.
Yeah.
Yeah.
Squared plus 36. You just calculate that.
Because if I change every x to an r squared.
And so that means we're gonna get a bunch of signs of both ends, so they're all imaginary, right?
You want to try to get the complementary?
Yeah.
I think it's good practice. I think it's good practice if you try. You sure? Yeah.
So I saw those.
Three I.
I had one of those, but it was made of like.
Okay, great, fantastic. Anybody need help?
I'm like right high, so.
Everybody doing okay? I like the roots there, good job.
Yeah.
Ooh, we have an issue with your roots here.
Is that
R squared plus 9, if I set that equal to 0.
No.
Did you have?
Oh, that's imaginary.
Yeah, you got some imaginary roots to
Man,
make.
that's a lot.
I wrote all this down.
Yeah, we gotta deal with some imaginary.
So you're really coding?
Well, actually.
Plus or minus
it's
five.
simple. The roots are correct, so plus or minus 3i here.
No, it should be 3i.
That's good.
Yeah, because I want to use a controller, but I don't know how to code it.
See,
And I was like, my friend doesn't know how to do it, so I was like, you know.
Oh, no, they're not squared, that's right.
So then I see like, a switch like that. Like the.
And that means it's.
C1, C2.
This is actually, there's nothing.
It's very simple.
No, I was thinking the other day.
This one would end up with 4 terms in our, so we have to try, these parameters.
I don't know.
We have 4 use.
Yeah, so we have not learned how to do that, so that's why we use that method.
Yeah,
Looking good, looking good.
Yeah, they're all clearly by pressure.
That doesn't like basically
Looks good, you have no repeats. Yay.
Wait,
Yeah, we gotta finish it, I guess. Because the reason
Yeah,
like,
Like candidates for R is like.
You gotta get your new
really
release.
think that, yeah, it's a multiple of that.
You said it earlier.
oh, that's fun.
Oh,
And
it's
then
just-
And then you gotta take
Negative
4 derivatives of that.
4?
Yeah.
No shot.
I've saved just enough class time today to take 4 derivatives of that. Give it a try, see if you can do it. You know, we may not get done, but this one is not so bad, because when you start taking derivatives, all that happens is factors.
Yeah.
It's actually not so terrible.
Y prime.
What about the negative version?
4a.
Negative 4.
You can just put like.
I literally write this on every test.
Yeah, there you go.
I literally write this like every single one.
That is. But then you get.
4.
No, it's minus 4.
Oh, I was right, okay.
Yeah, 4a.
4x.
Or the cosine.
It's not so bad. So, well, think about it. So if
This
it's,
part is like count 1 stuff.
Yeah, this is, I'm like enjoying this chapter because it's just all like
So
problem
what?
2. So I'm like,
the negative
Yeah.
e plus
So I'm like,
minus.
count 2 is
What is that called?
Cut is like.
Sorry, minus sign doesn't make sense.
I think we should, yeah.
So minus 16a. Cosine 4a. Cosine.
Yeah, use the 9 and the 4, guys, to try to get that thing factored down.
Like, you should have just said that.
Minus.
16b sine.
The derivative is gonna be a side note, it goes sine,
There we
cosine,
go.
negative sine, cosine,
Nice.
Nice.
Awesome, so then now you can get your roots. Looks good, looks good. Yay. Right, good job.
64.
This is beautiful. Now it's all a matter of trying to find it. Which is gonna be a little messy.
It's just like,
It's right, it's not too hard to take these right for.
Yeah, 256.
Ranking out these derivatives.
Cosine.
Wait, what about the e?
Minus cosine is sine, positive sine.
Oh, yeah, for I.
256. There's no e in I. Sine. Well, 4a is the ones in your head. And then, okay, so we write this out now. We get.
Later.
Then we're gonna take this and plug it into that.
We started to realize that.
Yeah, we only actually need this one.
Alright, cool, so for the other part. So,
Sine 4x. Kind of know what's going to happen.
so.
So I showed it all out here.
I forgot the
Yeah,
Yeah,
all these later examples.
15 times.
I'm pretty sure it was something like,
Anybody need
squared
help?
minus 16.
Going okay so far?
Just sine b.
Complementary function looks perfect, guys. Good job.
I
Good
don't
job.
like multiplying.
Uh-huh.
Right.
That's 208.
So that would basically just be.
Good job, guys.
6 of the y equal.
Which we already have there.
Sorry.
No, we don't.
like 50 times 4 is
Sine
40, and
times.
plus 16, get it to 6.
So all the cosines are zero. And all the sines.
She cancel loud.
So wait, we have 256. A.
So that means that A
No,
is
0
Great.
equals 1. This is minus.
Looks good. Looks good.
right.
This is a little bit harder than what I thought, yeah. But it's actually not too bad. I'm gonna get, oh, you already figured out 14, 16, 208. Yeah, you guys are doing great. All correct. That's looking good, guys. Good job. Now you realize what you have to do, though. 4 derivatives of that.
This is
I got
tedious more
a
than.
little bit
I feel like it's
ambitious
just more
with this
tedious more than actual.
What's this?
That's
one
right,
is this?
that's
is
right.
this.
Oh, wait, so 1 and 2, so 8. There you go.
Good. Let's do it. I'm gonna give you a little bit.
Wait, no, this one.
84.
Oh, yeah.
Wait, this means A is 0. I didn't have to do that.
You know, B is gonna be.
Oh, you're doing cosine, you just said A was 0.
It's just sine 4x.
But, So A,
I don't want to. I mean, cosine of 1 is 0, right?
yeah, you're just taking 0. Yeah, it's a 0 because there's nothing there.
A equals 0.
Yeah, equals 0, and then B is gonna be 1 over 184B. Since you're gonna get the same thing for sine, so 84 A sine. Oh, B, yeah.
Should be a B. There's no cosine,
B
right?
equals sine. Oh,
That's okay, I know what you mean.
yeah.
Looking good, looking good.
B.
What's multiplying this? It's one
Yeah.
B sine one,
Yeah.
right?
84
Are you guys pulling factors of 4 out and derivatives?
Ooh.
Oh, that's a good idea.
It's not only a good idea, it's like absolutely mandatory.
So B is 1 over 84.
Yeah, so hey, don't erase everything. No, don't erase everything. We're just gonna put a 4 here. And here.
Is this right?
And then by the time we
So-
go
Because
again,
there's no
we're gonna
cosine, so since there's no cosine, should be here. I assume that's right.
So our
finally, a 256. So those are the coefficients that you need in front of those terms. Otherwise, it's.
You
guys getting anywhere?
Yeah, plus 13.
Nice. And this is what we'll need, 16 times 13. We'll need
And
that
then,
eventually.
then just the final answer. But you decided this.
Times 4.
36y together.
But you know,
Y double prime.
yeah, you're good.
Yeah, no, it's the original.
So y p vex just 1 over 4.
I feel like this is wrong.
You can ask.
So I feel like this doesn't make sense when we just kind of use it.
16 times.
Well, then I'm just saying, I assume it's right, because like the original equation.
Yeah, there is
was
no
down.
cosine.
Yeah, so it has to be.
Cosine zero.
If there was a cosine, like I probably. But I don't see what you're saying, trying to take the inverse cosine. Inverse cosine is right. Why would you like to? Or something.
A cosine.
And then
Missing.
Wait, what the?
Zero
Oh.
over 1 times 4x.
That's this term.
What happened over here? You still know that 8 is 1 0.
Yeah, I
didn't do the Monday work.
it's so easy. It's literally brain dead. It's like, that was easy points. I didn't do it the whole weekend,
Oh, wait.
and I got home. I finished it like a half an hour. I didn't. He wasn't kidding. He would just bang it out. So what has that come for?
36.
I think that's right.
Yeah, I'm trying to do.
Actually, I mean, I don't know about that.
That's why.
What I gotta do is I gotta unite the cosine and sines together.
Because all of the terms that.
Plus 36.
So like, take all things cosine.
It's surprising.
I want to factor out the sine and cosine.
I'm just wondering how much Dr. B's gonna have to serve the class.
So you got.
It's exciting.
I'm sitting at like a B right now.
I'm like, I fucking suck at this. This is like, like freaking scores. And it's just like,
Okay, last week took me like turning out like 80% was like 70 or something. And the first one I turned out like
well, with the, I think the correction I got was like the correction. I'm hoping that I did better than this guy the last time, so it's gonna pump up another 10 points on my last time.
Yeah.
Okay, we have a question about.
That is the right answer, and that is also correct for A.
Yes,
A is the zero.
Yeah,
That's right. That's right. That's right.
Like, could we have told that from the start? Because there's no cosine. Like,
Yeah, you would sort of know that the A had to be zero. Definitely.
So if there was a cosine, we would actually solve it for.
Then we would have to solve for A and we get some other number for A.
You're right.
Yeah, that's right. Good job, really good job.
256.
Oh, we should have the exact same stuff.
You wanna take a picture?
No,
don't.
it's okay.
Let's go ahead and take a 10-minute break.
And the solutions are online.
Yes.
Legs outside, whatever, and then we'll pick things
Do
back
we even
up in
need to
about
do
10
it now?
minutes.
Whatever number we get.
Thanks for your hard work on
A
that.
is going to be A equals 0.
Break time it is.
Well, because there's no cosine involved. So it's well, B times that equals 4.
Yeah.
No, wait, equals
I don't want to
1.
do that.
And the 1 over that.
Too much.
Wow.
Good job, guys. Totally right. Great job.
Because you only have one sign over it, so it's gonna be there. It's gonna be whatever this is, yeah. It's gonna be 84.
Because it's 256 minus
Yeah.
208
Yeah, so sign.
plus 36. So 208
We'll
plus
take just a short break.
makes 240. Okay,
Yeah.
that's
You
four.
see it? So you get this out, so 84 being equal to 1. And then you're gonna.
You're so smart.
Very smart.
No, I'm not. It's literally just calculus.
Dang, just like that.
That's why I like this chapter a lot. It's just calculus a lot. It's so tedious more than actually.
It's interesting when you erase this, how you can feel the extra friction when you're going over.
Honestly, it's so satisfying.
No. Oh no, I left my lunchbox in my car. I wanted my Twix. Yeah, I wanted my Twix. I have a Twix bar.
Is it like crushed now?
No. No, so I left it in the car.
Oh,
So,
melted.
no, it's in the fridge.
That's still gonna be like slightly melted.
Oh, you know.
Yeah. Right, they're just asking for the annihilator, you're just gonna write it down. Yeah, good. Oh.
No, it's like a hitman story. I mean, or like rich people, but it's like a bunch of like one train going after one day. It's funny
All right, guys, I think I would like to go ahead and get started again. Thank you again for your hard work on the group work. Just a reminder that, in another few days or whatever, you might sort of feel like you need to review that group work, and that's certainly encouraged. Don't forget, the solutions are on my Canvas webpage. So all of those group works, when you do them in the real time, they probably make good sense, but then it's never a bad idea to circle back to them and take another look at them later. So that is about a wrap on chapter 8. We of course have a little bit of homework to practice on the variation of parameters stuff. But I would like to get back to what we were talking about on Monday, and this is really the end of the semester. Chapter 9 is where we're studying linear systems of differential equations. And specifically, I'm going to start off in these first few sections in chapter 9, just looking at a homogeneous linear system. So you guys remember on Monday, I wrote it out longhand. It took like the entire board and we wrote down all those messy equations. Do you remember what I said on Monday about that?
Making a matrix AX equals.
Right, I said I'm never gonna write it down again. It's way too much writing. So here is our nice compressed representation of our linear system. X prime equals AX. The matrix A right here, I should emphasize again here, this matrix is an n by n size. So we have a square matrix there. This is, by the way, this is the same recap that was on the sideboard earlier. I just wrote it back down again right here. And the first big result about this linear system is that the solutions form a vector space, or in other words, a subspace. Do you remember what it takes? Do you remember what you have to do if you want to verify that something forms a subspace or a vector space? What do you have to do? Goes back to chapter 4. Go ahead, Nathan.
Closure under addition and closure under scalar multiplication, it has 0 vector.
Closure under addition and closure under scalar multiplication. Exactly. And we can always start by checking the 0 vector as well. I am just going to jump right in to check. I would like to check that this is a vector space. So I am going to do that for you guys. This is a little bit theoretical, but I'm going to do it. We're going to check closure under addition right here. Okay, I just like to see how it looks when we write it down. So I have to start with two solutions to the system. Let's say we have X and Y and that they are elements of S. I'm going to give those names. Be sure to put arrows on the vectors. Anything that is a vector expression should have arrow on top of it. So let's say we take two elements of S. Again, what is S? S is the solutions to star, right? Okay, so what's that mean? This means that X prime is equal to AX and Y prime is equal to AY. Okay, so both X and Y satisfy my linear system. Now what I want to do is I want to ask myself, does X plus Y still belong to S? In other words, I'm going to look at X plus Y right now. I'm going to add those two things together. And I'm going to check, does X plus Y satisfy my equation? So if I take the derivative of it, right? I want to know, does it satisfy my capital A times the right-hand side? So what's the first thing that you would naturally think of to do here? You have a derivative of X plus Y.
Separate them.
Split it apart, right? Derivatives respect addition. So I'm going to write this as X prime plus Y prime. These are just derivatives. Remember, by the way, when you see the prime there, ooh, let's clarify this. That's a derivative with respect to what?
X, in this case, X.
No, it's not X. What are these?
OT.
That's right, T. Everything, remember the X is really X of T. And it just means it's a vector that's got, functions of T. This is what we wrote down on Monday that I swore I would never write down again, all of this messy notation. So the variable, although you don't see it anywhere on the board here, the variable that is underneath everything and behind the scenes is T. So these derivatives are with respect to T. Now, X prime, I already have been told that equals AX. And Y prime, I already am assuming that is the same thing as AY. And looking at this expression, what would be your knee-jerk reaction, what you would want to do? Factor the matrix out, exactly. The A comes out in front, let's do that. And we're left with the quantity x plus y. So look what we have. Blob prime is equal to A times blob. Anytime that's true, you're looking at a solution to your linear system, right? So this implies that x plus y is an element of S. We put a check mark there. So in a few weeks, we're going to be getting ready for our final exam, and we're going to remember hopefully how to check subspaces. This is the first part, closure under addition. Okay, great. Then we also want to check, just for the record, let's check the closure under scalar multiplication. I'm going to remind you how the write-up sort of looks for that. I start off by saying, you know, let x be as above. And what else do I need to do to set up the scalar multiplication part? You remember?
Okay.
We need a scalar, and I like to use k for that, and k is an element of the real numbers. So we grab a scalar k from the real numbers, and what we're going to do is look at k times x. I'm going to take the derivative of that. What's your, again, maybe somebody I have not heard from in a while want to tell me what happens when I take the derivative of this? What should I maybe do first? Separate it. And by separate it, you mean put the k outside, right?
Yeah.
It's just a constant, right? You're taking a derivative, you have a constant in front of something, you take the derivative of, you can just put that out in front. So we'll just pull the k outside. Great, and now we have k times x prime, but x prime is ax, right? We can replace the x prime with ax right there. And the k is just a number, so I don't really mind moving it inside. I can put the a out in front and slip that number inside. I'm going to put the k over here on the inside along with the x. So it's just a times kx. And now look what you have, guys. Blob prime equals a times blob. If we start from the left and go to the right, this is just the derivative of something equals a times something. So that implies that k times x is an element of S. So it is closed under scalar multiplication as well. Okay. So this really is a vector space. The solutions to our linear system, they really do form a vector space. Now, we haven't learned how to solve these linear systems yet. We're going to very shortly. We don't know how to solve them yet, but at least we do know that they form a vector space. Doesn't that mean that I should just look for a basis? We even know the dimension, don't we? It's an n-dimensional vector space. So we actually know how many basis vectors we should end up with. And that is going to be our strategy, guys, as it has been so many times in the past. Let's find a basis worth of solutions to our linear system, and that will therefore span the whole set of all of the solutions. Okay, is the big picture making sense? Of course, when you want to find a basis for something, you've always got to be a little bit conscientious about linear independence. Part of being a basis is that the vectors have to be linearly independent, right? They have to be a spanning set and they have to be linearly independent. I want to spend a minute to address linear independence, just like we had to do in chapter 8. We had to do the same thing. So the question here is, the question we're going to ask is, how can we tell if a set, and this set has vector functions in it. So I'm going to call it a set with x1 of t, and then x2 of t, and then we're going to go dot, dot, dot up to xn of t. How can we tell if that set is Li? So if I give you n vector functions, I would like to be able to decide if they are linearly independent or not. Because ultimately, if I'm looking for a basis for my vector space, I'm going to need to know that those solutions are Li. And this is not something, back in chapter 4, of course, we learned about linear independence and we were, working with numbers primarily that we could put into a matrix and solve it out. These are objects we've never worked with yet in this class. These are vectors, but not vectors of numbers. They are vectors of functions with t's in them. This is different than we've seen before. That's why this is a legit question right now. Like, we haven't learned how to deal with something like this. Well, it turns out that the answer to this question is the same answer that we gave in chapter 8. It's called the Wronskian. But I want to warn everybody, this is not the same Wronskian that we learned about in chapter 8. Now, the Wronskian in chapter 8, you remember how that worked? You had to, well, you just did this in a group work a few minutes ago, right? You have like e to the negative 2x and x e to the negative 2x. Those were like your first two functions. And then you just take derivatives down the matrix to get it into a square matrix. That is not what we're going to do this time. Okay, so let me explain this Wronskian. It's also called the Wronskian, but it's a different definition in chapter 9. So what it is, I'm going to call it W again, but it's a determinant. Actually, this Wronskian is nicer than the one we learned in chapter 8 because we don't actually have to take any derivatives like we did over here. All we have to do here for our Wronskian, guys, is lay our functions into the columns of this matrix. So you just lay them into this matrix in the columns, and you just take the determinant of that, okay? No derivatives are necessary. You literally just have to lay them down like this. Now, here is the theorem. The theorem is exactly the same theorem that we had in chapter 8, which is if there is a value of t, chapter 8 it would have been x, but in this chapter it's t. If there is a value of t, let's say t naught, such that, so if there is a value of t such that the w of x1, comma, x2, comma, dot, 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 and so on, up to xn of t naught. If there is a value of t, say t naught, such that the Wronskian is not 0, it's the same theorem we had in chapter 8, then my vectors are Li. Okay, so that's what we want to say here. x1 of t, comma, x2 of t, and dot, 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 up to xn of t. That set is Li. So this is the Wronskian test for chapter 9. When we were in chapter 8, we had exactly the same theorem, and we actually did, I don't know if you remember, guys, we did a group work where you guys, I remember how I led you, it was a long group work with the whole page was filled with like the step-by-step breakdown of the justification. So we've actually justified that one quite nicely in the group work. This one I'm not going to do as a proof either. I'm just going to state this, and let's just try an example. Okay, so let's just try an example. Let's let capital S be the set. I'm going to use t plus 1, t minus 1, and let me get the third vector that's in my example here. 2t, yeah, t plus 1, t minus 1, and 2t. And then the second vector is going to be e to the t, e to the 2t, e to the 3t. That's my second vector. And then for my third vector, I'm going to use 1 sine of t and cosine of t. Okay. I want you guys to just think of this as, this is x1, and then the second one is just x2, and then the third one is just x3. So we have the three solutions, x1, x2, x3, just listed like that. Okay, so the question is S Li or LD? Let's take a minute and talk about that. So I have my Wronskian test. I have my Wronskian test for this. So how does that look? We're talking about W, right? Is simply the determinant of a matrix whose columns are just those functions. So this is what I mean. This is easier than the chapter 8 Wronskian, because all you literally have to do is just copy everything into the matrix. First vector into the first column, second vector into the second column, and third vector into the third column. There's your 3 by 3 determinant. Now, we could just evaluate this determinant right now by using the arrow method for a 3 by 3, or we could do cofactor expansion along some row or column. That would be fine. It's gonna be messy. It's gonna look messy. If I leave this thing as is, it's gonna be a little bit messy. There's another approach that you can use at this moment, which is that you can say that the bar for linear independence is very low. And all that has to happen is you just have to find one value of t that makes this determinant not zero. So you could take a gamble and say, yeah, I don't see it off the top of my head, but I could try a value of t and just see if it works. Instead of like trying to, like if you write this out using the arrow method and get some big long expression over here, it's not gonna be very enlightening as to like what you should do. It's gonna just look like a mess. So instead of doing that, I like to sort of see if I can get lucky. Let's just try a value of t. And if I was just going to try a value of t to get lucky with, what do you suppose would be a good choice of a value of t to experiment with, Matt? 0 is right. So I could try t equals 0, and let's just try it. The reason is because it's easy to plug 0 into everything in the matrix there. So this is just going to be the determinant of, well, we get a 1, a -1, and a 0 in the first column. E to the 0 is just 1, so I'll fill that column with all 1s. And then 1, 0, and 1. Okay, and what we could then do is just now use the arrow method on this, and I will just save you the aggravation of doing it and tell you what the answer is. It's just 1. It's just 1, and that is not 0. Right? So it satisfies this idea that the Wronskian is not 0. Therefore, S is Li, and we're already done. So we just took a gamble and it paid off. We got lucky, and the Wronskian was not 0. Now let me ask you this question. If I had done this determinant right here, and if it was 0, what do you suppose we would have wanted to do next?
Try another value.
How about try another value of t? Exactly, we could think of another easy number like maybe t equals 1. And we could plug that in and see if that gives us a non-zero Wronskian, right? Remember, we only have to find one. If we find one value of t that gives us a non-zero Wronskian, we win, right? The vectors are Li, and we can just stop at that point. So we can try another value of t if the first one didn't work. Let's say we try the second one and it doesn't, but we still get a Wronskian of 0. Well, then you can say, all right, I'll try a third value. You can try a third value of t. Well, what if you get 0 again? What if you keep getting 0? You try it 3, 4, 5 times and the Wronskian keeps coming out to 0. You might start to see the writing on the wall. that maybe you're never going to find a value of t because maybe the vectors are actually LD. Right? That would start to creep into my thinking. If I've tried 3 or 4 or 5 values of t and I keep getting 0 for my Wronskian, I'm going to start to get nervous that there's no value of t that I could ever try that would ever work, right? Yeah,
It's
Nathan?
one of the few times where we could just keep working hard until we can't find a solution to prove that we're not.
You know what? We could try values of t from now until the end of the human race, and we would never have, that would not be approved, right? You could try 1,000,000 values of t and get 0 every single time. I'm still gonna go to you and say, oh, you just didn't try the right one. You didn't try enough examples. And so you can never really do enough of that. So what are you going to do if the vectors actually are LD? Like, you can't just say, well, I just keep getting 0, so they must be LD. Here's what you're gonna do. I'm gonna actually show you with an example. Right, so let's do one more example here. I'm gonna make this one a really obvious example. That even before we do the Wronskian, I bet you guys are gonna notice that these vectors are LD. So suppose I take t cubed, and then my second vector is -5t and -5t cubed. So you take those two vectors. Now you can probably tell that the second vector is just -5 times the first vector. So they're scalar multiples of each other. This is a classic case of when vectors are LD, right? So, but let's just pretend we don't know that, notice that. Let's just say is S Li or LD. Okay. So for our solution here, let's say we don't know, we just happen to not notice that these vectors are multiples of each other, and we try to do the Wronskian. Right, so the W, this is just the determinant of the matrix that we get when we literally just lay the vectors into those columns. And if I stop right now and I say, okay, I'm gonna start picking values of t to get lucky. And maybe I'm gonna get lucky and I'm gonna get a non-zero Wronskian. So you try t equals 0, and you plug it in and you realize, oh, the determinant is 0. Okay, so then you try t equals 1, and you get, -5 minus -5, oh, that's also 0. And you try any number of values of t, you keep getting 0. So you can't just keep trying values of t forever and think that that would convince anybody, because you can't check every number. But what you can do, guys, is you can hold your horses for a minute and you can say, wait a minute, I don't think this is ever going to work. So how am I going to convince somebody? Oh, let's just not plug a number in for t. Let's just do the 2x2 determinant formula here. And then we will see, I have a very little room here. If I just do AD minus BC, now from an algebraic perspective, I see that it all cancels out. No matter what t was, it's all canceling out. So that's how you would prove, so in this case, S is LD. It's not because you plugged LD, sorry. It's not because we plugged any particular numbers in there. It was literally just because we left it in terms of t and still got everything to totally cancel out. Okay. Guys, are there any questions on that Wronskian? Yes, Nathan.
Just like graphically, what would it mean for a system of differential equations to be linearly dependent?
Let's talk about that at another time. I've got about 5 minutes left. I've got to get through this. That's a good question, but it's not something I can answer very easily right now.
Sorry, just really quick.
Yeah.
For the one that you said that was Li, would you have done the same thing that you did for LD to Li and check that it's Li?
We could have worked out this determinant in terms of t, but you would have had to then convince me that it's not 0. Like here, this was easy to just see that it cancels out. This one is going to be much messier, and of course it does not cancel out. And so I would say this one is better to actually plug in a number for t. Yeah, definitely. Sebastian?
Could you do the algebraic thing as a check and then as long as there's still something left over?
Yeah, if you did the algebraic thing as a check and then thought, oh, well, now I see that I can plug in t=1 or something, and I'll get a non-zero Wronskian, that would be fine. Yeah. Okay, guys, I've only got a couple minutes. I want to say something about so everything I have set up to this point is 9.1, 9.2, 9.3, and that's all that you need for the homework you're going to do for Monday. Okay. I want to start, this is the big punchline. I'm not going to tell you the title of this section yet, because that will ruin the punchline, the fun thing I'm going to show you. I want to start solving these. We haven't been solving them yet. We've been dancing around talking about linear independence, talking about n-dimensional vector space. That's all theory. It's all good to know, but at some point, it's like, we gotta figure out how do we actually solve these things. And it's amazing what the answer is going to be. The question, before I get to the answer, maybe I should start with the question, which is, if it's an n-dimensional vector space, how do we get n linearly independent solutions to the star equation? How do we get them? And the answer is a thing of beauty. I absolutely love this. This is where the class starts to go back to some stuff we learned in the past, right? All makes sense. We're doing differential equations right now, but this answer is going to be linear algebra. Okay, namely, here it is. We're going to take lambda and v. Do you remember this topic? Wasn't that long ago, right? Chapter 7. This is an eigenpair of the matrix A. And what I'm going to do is I am going to form, okay, this is the big thing to write down here. I am going to make a solution. Now, again, I did not figure this out. This was way before I was born. We are going to form e to the lambda t times v. Okay, that is going to be the ticket to our success here. If we form this, we're going to get a solution to this. Can I show you? Can I show you? I'm going to take the derivative of this. I'm going to take the derivative of this, and it's going to be a times this. Watch. Let's check it. Let's check it. Let's take the derivative. I've only got 2 minutes, but that's all I need. It's really easy. It's not hard. So I want to take the derivative of this. Now, when I say I'm taking the derivative, of course, just to remind you, that is derivative with respect to t. So here, when I take the derivative of e to the lambda t, I just have to pull a lambda down, right? So the lambda comes down, lambda e to the lambda t. The v is just a constant vector on the end of that expression. All right. And I'm going to move the e to the lambda t by itself out in front and leave the lambda v in parentheses there. I could certainly do that. When you see lambda v, does that ring any bells of something from chapter 7? Yes. AV? AV. Somebody has remembered the most important equation in chapter 7. AV equals lambda v. Let's write that in here. Oh, this is so beautiful. I love how this comes out. So the lambda v turns into AV. And I can move the A out into the front because it's just a matrix with scalars everywhere else. And then we have the e to the lambda t. I'll put that over with the v. And look at that. That is just A times X. So look at my star here. This is the equation I'm trying to solve. X prime equals AX. Look what I just checked. X prime equals AX. It actually works. So this is amazing, isn't it? So now we're using chapter 7 to help us with chapter 9. Now, I don't want to take the air out of everybody's balloon right now, but just really quickly, I do have to point out that if we don't have enough eigenpairs, if some eigenvalue doesn't pull its weight, we might not be able to get n linearly independent solutions, which is what we need, right? It's n-dimensional, so we need n linearly independent solutions. So the bad news here is that this is going to be coming up short, unless, of course, we just make an assumption right here. I need you to write one more thing down for the day, which is in this section, which we will come back to on Monday, the matrices we are going to look at will always be non-defective, right? Do you remember what that meant? That just meant that every eigenvalue pulls its weight. It means that you'll get n linearly independent solutions that you can use as a basis for all of the solutions to this linear system. Is everybody a little bit excited about this? We're like seeing the linear algebra and the differential equations coming together kind of right here at the end of the semester. And next week, we're going to really talk about a lot of different things that are related to solving that differential equation. All right, folks, that's all I've got for you for today. Thank you for being here and have a great weekend. And we'll see you again next time. Crazy, crazy.